Hello everyone, Mrs. Sedlick here. I'm so sorry that I'm not in class today, but I'm going to walk you through the notes that are in 3.2. So make sure you turn to your new packet to 3.2. This is called Domain, Range, and Behavior. So we have two different learning targets. The first is one that we're going to spend a good amount of time together working on. And then the second learning target, I'm going to have you watch a video from Khan Academy and do some questions on Khan Academy. So our first learning target is to use set, interval, and inequality notation. So let's get started. So as a warm-up, students often struggle with the whole idea of what is an independent variable and what is the dependent variable. And if you're thinking about it on a coordinate plane, your x-axis is always going to be your independent variable. It happens regardless of anything else, whereas your y-axis is dependent. It depends on what happens with your independent variable. And students struggle with this even once they get to college, even once they take college-level math classes. So I'm going to try to sprinkle in some examples of this as we go through this particular unit. So our warm-up question says, the distance a car can travel is a function of the amount of gas in the car's gas tank. So, what is our independent variable in this type of scenario? Well, the independent variable is how much gas you have in your tank, right? The dependent variable is your distance because how far you're able to drive depends on how much gas you have in your car. So that's often something that I tell students to say is, write the scenario with the word depends. That tells you that since distance depends on gas, gas is my independent variable and distance is my dependent variable. Our second warm-up question talks about all these different words that we have for different numbers. And you'll notice that I'm only talking about the real number system. For this particular unit, we're going to kind of forget that I exist and we're going to focus mainly on real numbers. So when we talk about all the different categories of real numbers, we have all these vocabulary words that you might see. So let's make sure that we define what each of these are. And you'll notice it's kind of like a Venn diagram, meaning if it's a natural number, it also could be considered an integer, right? We kind of work our way from the inside out. So let's talk about what the natural numbers are. Well, the natural numbers are whole numbers, positive whole numbers like 1, 2, 3, 4, etc. The difference between the natural numbers and the whole numbers is really just with whole numbers, we add in a 0, 0, 1, 2, 3, etc. And the reason that natural numbers don't include 0 is a long time ago when numbers were first being developed by humans, they were terrified of the number 0. The number 0 did not make sense to them. And in fact, it's quite a bit of an abstraction for people to really understand what is 0. So they considered 0 to be weird and kind of evil for a while, and so that's why it's not included in the natural numbers, but it is included in the whole numbers. Now integers, those are positive and negative whole numbers, so it could be -5, -99, or it could also be 6. 146, right? It could be both positive and negative whole numbers. Now, a rational number is a number that I can write as a fraction. So if I'm able to write it as a fraction, it is a rational number. You know, sometimes on our calculators, we might hit math enter, enter when we get a very gross decimal. And sometimes our calculator can rewrite it as a fraction. That would be a rational number, and sometimes our calculator just can't write it as a fraction because it's an irrational number. So some other examples of rational numbers, we don't always see them written as fractions. It could be something like 0.6 repeating, right? 0.6 repeating is 2/3. So as long as I'm able to convert it from a decimal to a fraction, it is a rational number. Irrational numbers are numbers that we cannot write as fractions. So things that students often think of, like pi, for example, 3.1415, yada, 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 we cannot represent pi as a fraction. We can estimate it, but we can't actually take the actual value of pi and write it as a fraction. Same thing as like square root of 2, right? We just got done with a unit that had a lot of square roots in it, and a lot of the square roots that we covered cannot be written as fractions. So that concludes kind of our warm-up section. Now let's move on to our first learning target, which is all about how to write things in different notation. Now, writing things in different notation is not usually any student's favorite part of Algebra 2, and I get it. It's almost like this is the vocab, this is the way that we write things in math. Now going forward, you will see these types of notations if you go on to take pre-calculus or even discrete math or even statistics. So these types of notations are kind of the building blocks. If we don't understand how to read these notations, it's going to be really hard to work with a textbook in the future. And I'm hoping that all of you have seen this inequality notation before, right? We've got less than, we've got greater thans, greater than or equal to, less than or equal to. So I'm hoping that this column here you have seen before. These two columns are probably the new ones, something new that you haven't seen before. So we're going to practice a bit with them. This first page of your notes, though, talks about how do I say these out loud? And I want to make sure that you understand like how, if I were to say it out loud, what it would translate to. So we're going to look at just this first row here, and we're going to use that as our example, and I'm going to say out loud how I would say it, and then we're going to write it down exactly how I say it. So in our first one here, this inequality notation I say out loud as x is greater than or equal to a and less than or equal to b. So let's write that down. X is greater than or equal to a and less than b. Less than or equal to, don't want to forget that, right? Because both of them have those equal to signs, so I have to consider those and write those down. Now let's move into our new notation, our first new notation, set notation. It's got these curly braces. It's got what this is called here is a pipe. If you look at it on a computer, it's the up and down symbol that's right above your enter or return key. So how do I say this one? Well, it's just the same as inequality notation. I just happen to add some wording to it at the beginning. And it's the set of all real numbers such that x is greater than or equal to a and less than or equal to b. So you'll notice I repeated this whole wording here from inequality notation. The only thing that I said differently is the set of all real numbers such that, and then I repeat what I have up here. So I repeat that whole phrase. And I know maybe you've seen this kind of strange R. That stands for all real numbers. So there may be times where you are asked, what values of x can I plug into this function? Well, maybe you can plug in anything you want for x. You might say it's just the set of all real numbers, and you can write it as a big R with a double line through it. Our last notation is this interval notation, and I have a feeling at first you're not going to like it, but then you're going to notice just how short it is, to write. I find that most students by the end of this unit prefer using this notation. It takes some getting used to, but let's talk about how I say this type of notation out loud. You'll notice that I have two brackets here, one on either side. So a bracket, that tells me that I want to include. So in this case, I want to include A and B in my interval. You'll see on some of the other ones, I have a parentheses. If you see a parentheses, that means we do not include. We do not include A, or in this case, infinity. So those are the difference between the brackets and the parentheses, and we will get a good amount of practice with these. So just hold tight and stick with me through this. I promise you'll get used to this notation here. So the way that I say this particular notation here out loud is I say all real numbers from A to B, including A and B. So all real numbers from A to B, including A and B. Because the brackets tell me I include and the parenthesis would tell me I don't include. So that is how we say these intervals out loud. Let's go ahead and flip to our second page, and we're going to get some practice with how to write certain things. Once they're graphed on a number line, those are our solutions to some particular function, we're going to then write them in the different notations. So you'll notice in my interval here, first, these are both examples of what we call finite intervals, meaning they have a start and a stop. I'm not shading in the arrows, right, to show that I'm going all the way down to infinity or negative infinity. So when they're finite, they have an actual start and a stop location. So in this case, my solution to whatever the function may be or whatever the equation may be, you don't have to worry about what the starting is. We just have to worry about, okay, now I've graphed the answer on a number line. How do I write this number line in our different notations? So in inequality notation, I want to make sure, and you can use any variable we want. We always usually use x, but you don't always have to use x. I want to say that x is going to be greater than or equal to -2 and less than or equal to 3. So I would write that as -2 less than or equal to x less than or equal to 3. Since it's an and statement, I want to include all the things within here. I write it as what's called a compound inequality, where I put my variable in the middle and then I have less than signs on either side to kind of encompass that entire portion of the number line. For set notation, I already have my inequality piece done, so all I really have to do is add that wording. For all real numbers x, such that, that's kind of what the pipe means, and then I fill in the inequality that I'd already set before. Last but not least, we have interval notation. This is the short one. I really just have to figure out, I know my start and my stop, it's -2 to 3. Do I include -2 or 3? Now a closed circle, when it's shaded in that way, that means I include it. Whereas if it were an open circle, not shading, that means I don't include it. So you just have to consider those two options and kind of know how to connect those. Since I want to include both -2 and 3, I use brackets around the outside. I highly recommend you pause the video now and try this next one on your own before I fill it in. So this next one is pretty straightforward. It's very similar to what we did here. The only thing that I have that's different is I don't want to include -2. So when I write my inequality, I'm not going to put the equal to symbol in here. I'm just going to leave it as x is greater than -2 and less than or equal to +3. Once I have my inequality notation down, I can go ahead and write for all real numbers x such that x is greater than -2 and less than or equal to 3. Last but not least, we have our interval notation. So I know my start and my stop. Now I just have to figure out, do I use brackets or parentheses? Since I don't want to include -2 because it's an open circle, that gets a parenthesis, whereas since I do want to include 3, that gets a bracket. And I know it's going to look strange to you. You may not like it, right? They're kind of uneven, but that is how we write that particular notation. Now let's look at an example where I have an infinite interval, where things go on and on and on forever, right? I'm shading everything in down here, and I'm shading everything in up here. There's a couple different ways that you can write these notations, and I just highly recommend you go with the one that you like the best. Normally, when you were in Algebra 1 or even middle school and you saw a number line like this, you would say that the solution is everything that's less than or equal to 2. So you would say x is less than or equal to 2. Now, sometimes students want to kind of go with the whole, well, I want a start and a stop. If I'm always writing it the same way, why can't I just figure out a start and a stop? And in this case, my start would be all the way down here to what we call negative infinity. So I would have negative infinity less than x, which is less than or equal to 2. So these are two different ways that you can write this. Now you'll notice I cannot ever be equal to negative infinity. Infinity is this abstract idea that I will never reach, right? So because of that, I can never have an infinity be equal to. So these are your two options. Pick one that you feel you're most comfortable with, because once you figure out your inequality notation, the set notation falls right in line, right? For all real numbers x, such that x is less than or equal to 2. Or, right, for all real numbers x, such that x is greater than negative infinity and less than or equal to 2. Last but not least, we have our interval notation. Now with interval notation, you have to have a start and a stop. So in our case, our start is negative infinity and our stop is 2. Once I figure out my start and my stop, notice I always put the smaller number first before the larger number. I just have to figure out, is it parentheses or brackets? Well, since I can never get to negative infinity, that's a parenthesis. And because I can get up to 2, that is a bracket. All right, again, I encourage you to pause the video now and try this next section on your own. But let's move on for those of us still here. So here I have basically everything that's to the right on my number line shaded. And if you were in Algebra 1 or in middle school, you would have written this as x is greater than 0. Notice it's not equal to because I'm not including the number 0. Now, another way that you may want to write it, right, because you may want to say, well, I like the whole start and stop idea. I know I'm going to need it when I get down to interval notation. So in this case, we go from 0, we don't include the 0, but we go all the way up, but don't include positive infinity. And yes, I know this infinity symbol takes some time getting used to. You don't need to put the positive sign there. I normally do that just so when students are taking their notes, they can easily distinguish between the negative and the positive, but you don't need the positive symbol there. So these are your two options. Pick which one makes the most sense to you, and then for your set notation, for all real numbers x, such that x is greater than 0, or our alternative, right, for all real numbers x, such that x is greater than 0 and less than positive infinity. If you do choose this second option, your interval notation becomes a little bit easier. You already know what your smaller number, your start, and your stop are, and then you really just have to figure out, is it parentheses or brackets? Well, it's a parenthesis for 0 because I don't want to include it, and it's also a parenthesis for positive infinity because I can never actually get to positive infinity. Right, moving on, we have a couple more examples to do. So we have a number line, and everything here is shaded. So you would just say, and many textbooks, math textbooks use this, would just say, this is just all real numbers, right? We're including everything on the number line, so that's just all real numbers. Well, how would I write that as interval notation? What is my start and what is my stop? Well, I'm going from negative infinity up to positive infinity, so it's negative infinity to positive infinity, both with parentheses. That's how I write all real numbers in interval notation. Looking at this next example, I'm including all real numbers except 0. So that's normally, right, how we would kind of say it out loud. So we would say all real numbers except 0. Well, how am I going to write this as interval notation? This is a pretty tricky one. What we basically want to do is we want to say, okay, here's my start, and then here's my stop. And then I also have another start and another stop. So I actually have 2 separate intervals that I need to include. So what I do is I take this first interval. I go from negative infinity up to 0. I don't want to include 0, so it gets a parenthesis. For my second interval, I want to also start from 0 and go all the way to positive infinity. Again, both with parentheses. Now, normally, maybe you want to just put the word and in here or put an ampersand. Well, in math, right, of course, we have different symbols, and the symbol that we use to show the joining of these 2 intervals is called a union. So it's the letter U, and it just stands for basically a combination. I'm combining this interval and this interval to give me the entire interval notation that represents the solution. All right, so we're going to go through some of these examples here at the bottom on end behavior, but I'm really expecting that the video from Khan Academy gives you more in-depth information than what you see here. So when we come back to class together on Thursday, we will practice quite a bit with end behavior. We'll play a little end behavior game. We'll kind of get used to this notation. But for right now, let's talk about what end behavior is. So first off, what's this little symbol mean? We've been talking about it already, but I want to make sure you have it in your notes. It means infinity. It's just a number 8 on its side. So what we do when we explain the end behavior of functions, we say, well, as x gets bigger, what happens to my y value, right? As x gets bigger, what happens to y? That's really all end behavior is. Now, of course, because we're in Algebra 2 and we're kind of getting used to some of this new function notation, which we saw in 3.1, instead of using y, I'm going to use f of x. It means the exact same thing. So we're going to say as x gets bigger, and instead of getting bigger, we're going to say as x approaches, so we're going to use an arrow sign to represent the word approaches. As x approaches infinity, what happens to y? So let's look at this example up here in the top left of this table. Over here, you'll notice as my x gets bigger, so if I trace my x, what's happening to my y? Well, my y value is going up. So it says as x approaches positive infinity, so does my f of x. It gets bigger. Down here, I have as x approaches negative infinity. So as my x goes to the left on the number line, what happens to my y? Well, my f of x, my y, also approaches negative infinity. And if you look at these other examples in this table here, you'll notice that they have kind of been outlined and defined based on the categories here. Now, I don't necessarily want you to kind of memorize these, right? If the degree is odd and the leading coefficient is positive, then yada, yada, yada. You might memorize those if you go on to pre-calculus, but for right now, what I'd like you to do is get a visual of what we're talking about. So the function here is asking, if I have f of x is equal to x to the 7th plus 3x to the 4th minus x squared, what is my end behavior? Well, I need to see what it looks like. So what I'm going to do is I'm going to pull up Desmos or pull up my graphing calculator, whichever you're more comfortable with. So let me go over here and pull up Desmos. Click on graphing calculator, and I'm going to type in the function as it looks. So I have x to the 7th power plus 3x to the 4th power minus x squared. I now have a visual of what this function looks like. And it's a pretty ugly function. We're going to study quite a few different functions this particular unit, and not all of them look the same. So what I see here is that as my x gets bigger, so I'm going to kind of trace my cursor along the function. As x is getting bigger, what's happening to my y? Well, my y value is also getting bigger. Now let's look this way. As x gets smaller, so as x becomes more negative, what's happening to my y value? Well, it's also becoming more negative. So let's go back over to our notes and fill in that information. So as x became more negative, my f of x also became more negative. So f of x approached negative infinity. Whereas when x became bigger, when x became a bigger number, my f of x also became a bigger number. So f of x approached positive infinity. Like I said, the Khan Academy video should hopefully help out a little bit with practice